We have a Lucy.
From Cinderella.
Anna Jackson. We had a baby kitty that showed up this week, about this big. His head was this big and his body was this big. But we put out a call to the neighborhood and someone came and picked him up.
Is the guy on your YouTube channel who talks about MRIs he your son, by chance?
Yeah,
He is?
yeah, that's my son.
Okay.
You seen the video?
Yeah, I looked over it and I noticed he had the same last name, so I was thinking.
Yeah, that's my son. Yeah. He's at Georgia Tech. He'll be a senior this fall, but he's in California this summer, interning at Apple.
Wow, that's impressive.
Right. Well, it's Stevens' son.
Yeah, that's
true.
Like, come on.
Yeah.
Cupertino. Okay, mass spec is here. You got the mass spec handout. Any questions about mass spec yet? Any questions about mass spec yet? You've been watching mass spec. There are problems in this handout. Only one page of problems. Most of the problems are going to be in the workbook. But in the back, a little bit in the back is this page here with the 3 hand-drawn compounds. Okay, please try to be doing this one. We will do this one in class. Maybe tomorrow or definitely by Friday. Dienes, chemistry of dienes. Then we'll be moving to the pink handout, substitution reactions. Let's see how we did here. Any questions about the the 1-2 or 1-4 additions? The answer key is in there. Any questions about these?
So when you look at like the most stable one between two different like possibilities, alkene stability trumps carbocation like stability?
No, carbocation is intermediate. Alkene would be the final product I reckon you're looking at.
Right, but like for number 2, there was a tertiary carbocation and a secondary alkene, and then the other option was secondary carbocation and trisubstituted alkene.
No, you shouldn't be combining cations with alkenes. First choice is which cation we're going to make. Which allylic cation you're going to make. That is, which alkene is going to react with the HI. In this example, I can tell it's going to be the alkene on the right. Because I draw reaction of both. With both, you have a resonance structure. But then you assess both hybrids. Once you determine which alkenes, which cation is going to form, you get rid of the other one. Then you work with this carbocation, the hybrid. Then you can get either the 1-2 or the 1-4 addition. Just like we did on number 1. We should not be comparing cations and alkenes together.
Okay.
So keep at it. I mean, first thing you gotta do is look at the two different cations that we form. Not alkenes. First thing is cations. You gotta decide which cation is gonna form. And that has nothing to do with alkenes. That involves cations. That's the first step. Keep looking at it, keep asking. Other questions about that page? Did you check your answer?
Yes, I was getting them right, but, yeah. I meant like when you choose between the 1, 2, and 1, 4, would you, like, how would you decide which one's most stable? That's what I meant.
How do you decide what's most stable?
1, 2, or 1, 4.
Yeah, but what are they? What are you looking at? What is
The two different resonance structures.
two different what?
Resonance structures.
No, those are not resonance structures. Those are your products. Your products are alkenes. How do you determine stability of alkenes? We did this last week at about 10:40 one day.
Substitution. Or substituents, I mean.
I really shouldn't have to answer that. How do you determine stability of alkenes?
Number of
Two different alkenes. How do you determine which one's more stable?
Number of substituents.
One what?
Number of substituents.
Okay, so that's not difficult, right? Well,
Right.
you have two alkenes to compare?
Yes.
Which one has the most carbon substituents on the alkene?
The 1, 4 product for second column.
Okay, then that's the most stable.
Okay.
Just like we did the first one. If you need to look at the video, we did everything with the first one, everything. We did stepwise, systematic. How do you do it? At that point, you're not looking at cations. The reaction's done. You're looking at... Okay. Question?
When it's cold, it's always going to be the 1, 2 product.
I can't
If it's cold, is it just always going to be the 1, 2 product?
Yes, if it's cold, it will always be the 1,2 product because of the proximity effect. The nucleophile is closer to the H. The H added at 1 is closer for the nucleophile to add at 2, because that's where it is. To get over to 4, it's a cross-country trip. That requires higher activation energy. Cold temperature, you don't have much energy, so you're not going to be able to do that. Even if you did, it's still faster to get to 2. So you're going to get the 2 first. They will form first. But with heat, though, it can come back off and equilibrate, and you'll end up with 1,4 because of 1,4, well, not always, but sometimes the 1,2 is the most stable. Other questions about 1,2, 1,4 additions? Finally, you just got to figure out what you're trying to ask. You're combining two different points. Okay. Diels-Alder reactions. Any questions up to where we're at? Okay, I think we left off here. Yeah, we're looking at which product we're going to form. Because neither one of these is symmetrical. If either one is symmetrical, we don't have to worry about it because you can do it like this or that, you're going to get the same product. When both are non-symmetrical alkenes, or when the alkenes are not identical, here, or that's not symmetrical, you got possibilities because this can be like this can be flipped up or down, or this can be flipped up or down. We showed this last time. With the withdrawing group, the withdrawing group polarizes this. Resonance structure. We talked about resonance structures of neutral molecules. The oxygen is electronegative, so we have, intuitively, we can say electrons are moving towards the oxygen. We can move these up, we can move these up, we can get partial plus here. That's always the case. Especially when you have a carbonyl or nitrile. Carbonyl is most common. It could be a variety of functional groups. It could be aldehyde ketone. This is an ester. This is going to lead to the beta carbon being partial plus. First carbon coming away from the carbonyl is alpha. The next one's beta. And the next one would be alpha, beta, and if there was a next one, it would be gamma. Okay? That may come up with mass spec. Here, the beta carbon is always partial positive. Over here, which N carbon is partial negative? Because that one will bond here. Resonance. Can you draw a resonance structure of that molecule? Where do you want to start with? Lone pair is a great place to start with resonance if the lone pair is conjugated. What type of orbital is one of these lone pairs in? One is at a p orbital because there's a p orbital next door. We can do resonance. These electrons can move here, and these can move out. We can get this resonance structure. We can keep going. These electrons can now come here, and we can move these out. No change here. Everything is shown by your arrows. This arrow means pi bond is now here. And this arrow means you now have what? Lone pair there. Okay, the true structure is a blend of these. Which one of these three is the best? Or major resonance structure? Should be easy. Which of the three is the best resonance structure?
The original one.
This one here. Charge separation is typically not good. That does not mean that these do not contribute. All resonance structures contribute to the true resonance hybrid. So we can look at these and say, okay, in the true resonance hybrid, the true structure, which N carbon has some partial minus charge?
The top.
So you look at your resonance structures. Which one takes on negative charge? That one. Does this one here ever take on minus charge? No. This is partial minus due to resonance. The lone pair here is effectively increasing the electron density here. We see that from this resonance structure. This is like a garden hose full of water. But electrons are like, when we're talking about electron density, lots of electron density here. Like lots of water in the garden hose over here. But that water is going to spread out if it can. These electrons are spread out through here, and it's really, there's a lot down here. There's more theory here. Again, we look at the resonance structure. That carbon has partial minus. These two carbons are going to bond together. Because physics tells us that partial minus is going to be most attracted to partial plus. These need to be flipped over. I need to flip this guy over. I'm going to draw it right here. Flip it over and have the methoxy here. Partial minus on the other end. These bond together. Flip them together, which one you're going to get? On the right. Yes, that's the product. Resonance. saw resonance with 1,2 direct addition, 1,4 conjugate addition reactions in this handout. Now we're seeing resonance with Diels-Alder and predicting regioselectivity. What's the relationship between these two products? Potential products? This one's going to be formed, but what's the relationship between these two potential products from this reaction? What's the relationship between those two structures?
Constitutional isomers.
Yes, they're constitutional isomers. They have different connectivity, different names. But in the context of that reaction, what can we call them?
Diastereomers.
I think we use this term with alkene reactions.
Is it diastereomers?
No, those are not diastereomers. Diastereomers are stereoisomers. Those are not stereoisomers. They're constitutional isomers. Regioisomers. Things are bonded in different regions. Regio is in the context of this reaction. If you just showed them by themselves, you would just call them constitutional isomers. Which regioisomer will be formed in this reaction? The one on the right. Thus, yes, this reaction is regioselective because of resonance influences. Okay, there's two others for you to work. Up here I gave you two possible. Down here I'll let you just show the product. This one's easy. That's the same thing. It's partial plus, right? It's the same exact thing, right? Okay. Mainly it's practicing resonance structures and seeing where the partial plus and partial minus is. Very important tenet of organic chemistry, resonance. Right up there with hydrogen bonding. To explain a lot. The synthesis of Tamiflu, drug to treat flu. Compound 1 at the bottom. It begins, it's a long multi-step synthesis. It begins with a Diels-Alder reaction. Furan, iodine. You can use catalysts with Diels-Alder reactions. Making this product here with this bridged oxygen, yeah. They're showing it back here instead of forward, exo-endo, that's the relationship between these two. But it's racemic. Then they actually separated enantiomers to give only the LEVO product. But the first step is the Diels-Alder. And a Diels-Alder gives what type of product?
6-member group.
What type of product does a Diels-Alder give? Cyclohexene. It gives a cyclohexene. You see the cyclohexene in there? Yes. 4 plus 2 is 6, right?
Yes.
Reaction on the back. Sort of a little application here. Prostaglandins. Prostaglandins shown down here. They're very important biological molecules. Leading to inflammation, pain. Sounds like bad stuff. Aspirin used to treat inflammation and pain. Drugs like aspirin. Aspirin inhibits the COX enzyme. It inhibits this enzyme here, Cyclo Oxygenase, COX. This enzyme in your body converts arachidonic acid to this guy. What's going on here? Arachidonic acid reacting with oxygen. Okay? I assume you breathe in oxygen, yeah? Okay, there's reasons for that. This means oxygen here. What's going on? The chemistry is right here on the end. 2 oxygens. 2 oxygens, that's a peroxide. This is called, in part of a ring here, it's called an Endo Peroxide. Kind of an unusual little structure here. But it continues on. What's going on here? Let's look at this. It's almost like a Diels-Alder reaction, but it's not exactly. But it is a Cyclo Addition. Because it's a cyclic transition state and we're making a ring. We have oxygen. We can draw it as a double bond. And we can move electrons. These electrons move here and attack the oxygen. These electrons come down here. And then these move up to replace where that left. Okay? What does all that arrow movement give? Hopefully you see it gives that structure below. You got to see arrow movement. All right? That's a Cyclo Addition reaction. Not exactly like a Diels-Alder, similar. There's variations on Cyclo Addition reactions. More generally, these are called pericyclic reactions, and there's often textbooks will have chapters on pericyclic reactions. A Cyclo Addition is one type. That's another type of pericyclic reaction. Pericyclic reaction is a reaction that just has a cyclic transition state. So, sort of an application, not exactly Diels-Alder, but aspirin. This is helped by an enzyme. Enzymes act as catalysts. How do they do that? Well, beyond what I can show you here, I don't know. I have to look it up, see what's known, if it's fully known. But it is known that the enzyme does it. The enzyme is named. Aspirin inhibits this enzyme. And so when you take aspirin, this is not converted to that as much. You get less of this. Because you get less of this, you get less of these. And so you get less inflammation and less pain because these help lead to inflammation and pain. All right? So that's an example of a drug inhibiting an enzyme. And thus inhibiting a process. Okay, that's dyeing chemistry. How we do on the front? Yeah, HBr cold and hot, seem reasonable. Which drug below could be made using a Diels-Alder reaction? Which one looks like it could be made using a Diels-Alder reaction? Oh, well, we just looked at it. Tamiflu, right? Why? Cyclohexene. Diels-Alder doesn't give a 5-membered ring, well, you can make benzenes from cyclohexene, but right there screams Diels-Alder, right? We covered dienes. Is this a diene or what? What is that? Triene? Tetraene? It's a pentaene. Yes, 5 alkenes. 1, 2, 3, 4, 5. Usually when you get above maybe 2 or 3, you start calling it just a polyene. Multiple enes. Polyene. Yeah? Polyene. Amphotericin. Ever heard of amphotericin, antifungal drug? Would you call it a polyene?
Yeah.
Yeah, it's a polyene. There's a variety of other structural features to it, but it is a polyene. Okay. Well, stereochemistry. What functional groups do you see? Final exam's coming soon. Alcohols or hydroxyl groups. What else? Ester here. Where do we see an aldehyde?
Ether.
Carboxylic acid,
Amine.
amino or primary amine, ether, cyclic ether. This is a cyclic ester. Ester, part of the ring. That's a big ring, yeah? Cyclic ester is called a lactone. Lactone. You might hear that in organic too. Okay, that's dienes. Okay. We're now set to start one of the most important topics of organic chemistry. Substitution reactions. The next handout will be elimination reactions. Okay? Go ahead and pass that one out. Substitution and elimination reactions. Our alkene reactions, very important. These reactions even more so. Well, even more so in real life. In courses, they're both equally important. In practice, these reactions are much more versatile. Much more versatile. These reactions will also be more general. We learn general concepts, and then we need to apply them to individual reactions. Alkene reactions, you can memorize it a little bit. Alkene reacts with a bromine and water to give what? Halohydrin, the OH and the bromine will be anti, etc., etc. Okay? You can sort of boil it down to that reaction. You can't do that as much here. You got to be able to assess a broader assessment. Okay, here's some types of reactions. Substitution reactions. This is a substitution reaction. The OH is being replaced with the bromine. And Gen Chem, I think you called substitution reactions replacement reactions. Is that right? Okay. Analogous term, but we say substitution. We're also dealing with covalent bonds, not ionic interactions. Okay? So we can't say replace. The bromine has replaced the OH. But we will say substituted. Okay? With alkenes, we were doing what type of reaction?
Addition.
Addition. You take an alkene, you add something to it. You don't replace anything. Here we're replacing, we're substituting. All right? Here's a general line reaction. We have some type of, what is X? Leaving group. LG, I will say. Some type of leaving group. Now, X is often typically halogen. And halogen are your best leaving groups. But here I'm doing even more general, this being leaving group. Okay? We got a leaving group on a tetrahedral carbon. Alright, headings are very important. We've got some type of nucleophile with typically a lone pair. Okay? And the nucleophile will replace the leaving group on the tetrahedral carbon. The leaving group will leave. That's what leaving groups do, right? What do leaving groups do? They leave. That's why we call them leaving groups. And it will take a lone pair with it. I'm not showing how many this had. If this had 3 to begin with, how many does X over there have now? 4, because it takes another lone pair with it. I'm just showing the lone pair. Okay? That is, these 2 electrons here go with the leaving group. That's where the lone pair comes from. That's a generic substitution reaction at a tetrahedral carbon. All right? Most common leaving groups are halogen, with the best being iodine, then bromine, then chlorine, and then fluorine is the worst. And it's typically not a leaving group. We will go over leaving group ability. Which one's the best?
Iodine.
Yes. Other atoms other than halogen can also be leaving groups. Here's a specific example. We can take this alkyl bromide, react it with hydroxide. The hydroxide has replaced the bromine, yeah? The bromine has served as a leaving group. The bromine has 3 lone pairs here. It takes on another lone pair, right? When it takes on another lone pair, now it has 4. This charge is now minus. Over here, this charge was minus. The good old-fashioned substitution reaction. Leaving group chemistry. Let's show a mechanism for this reaction. How does this take place? Magic? No, we only have 1 or 2 magic reactions in the course of, we're getting 1, we're getting 2. Actually, every other reaction we're going to do full detailed mechanism. Possible mechanisms for this. Now, I've already sort of named them a little bit, so I'm going to have to do one possible here and here as opposed to just saying, doing it randomly. I'd like to hear from you. What can we do here? What do we need to do? What could be a first step, or Maddie?
You could transfer the electrons on the bond from the carbon to bromine onto bromine.
These electrons go here.
Yeah.
Let's do it right here. Let's do it right here. Same thing. These electrons go here. What does that do? That's going to give this with only 3 bonds. There's 2 H's here. That should be a plus. And what else do we get?
Minus.
Br.
Minus.
Electrons move here. There's 3 lone pairs. That's minus. Hey, we made one thing. Br minus is now made. We just got to make both things.
Attack to use the electrons on oxygen to attack the
These electrons make bond here. These electrons make bond here. What does that do? Yes, there you go. I mean, what else do you need to do to get over there? Nothing if you do that there. These 2 arrows are not mechanism errors. This is a reaction progress arrow. This is mechanism. Sometimes mechanism errors need to be a little more curvy. keep them from, this is so long. Okay, yes. What do you think about this mechanism? First off, what is he, let's name each step. What do we do in the first step?
Leading group.
Leaving group left.
We can say LG leaves. What else can we call this?
Carbocation formation.
We can call it carbocation formation. What else can we say happened here?
You got a bromide ion.
Just tell me again.
You got a bromide ion now.
Okay, you're onto something here. You made a bromide ion. We also made a carbocation. We made two ions from a neutral. What do you want to call this?
I don't care.
No, I thought you almost had it. If we take HBr and put it in water, it becomes H plus and Br minus. What do you want to call this?
Ion?
Ionization. Yeah, and that, can't we call it that? Ionization of the bromide to... Yes. What do you want to call the next step?
Substitution.
Nucleophilic addition of Br minus to carbocation. Basically, nucleophilic addition, that's underlining. The nucleophile adds to the cation. What's the definition of a nucleophile? What is it like? It likes nucleus. No, that's just a roundabout way of saying it likes positive charge. The nucleus is positively charged. I'm sorry, why did someone correct
Oh,
me?
oxide, right?
What?
Oh, it should be OH.
The hydroxide is the nucleophile. The bromide, the bromine was the leaving group. Okay, reaction coordinate diagram. For our mechanism here, we start with A, starting material, organic starting material. How many intermediates? One, it's called B, and then final product C. Okay, if we put these over here, okay, you should label these as usual. This is A, some arbitrary energy level. Where's B going to be? Higher. It's a charged intermediate. It also doesn't have an octet. It's going to be higher in energy. Where's C going to be? This is tough because before we were going from maybe a pi bond to a sigma bond and we can sort of intuitively tell. It's tough to tell where C will sit. You're going to have to really get out a calculator and see bond strength. It's not easy to see. I'm just going to draw it about here. It's probably a little bit lower, but I don't know that I would expect you to know that right now. Okay, here we go. How do we go here? Just straight there? No, we have like this, right? Transition state fall into an energy well for the intermediate. And this is where it sits. There's a transition state leading to this, right? Here it is, the bromine leaving. It's got a break. That's a transition state. Then from here, what type of transition state is needed to go downhill? Usually not much. Just a little bit. Yeah? Which step should be the rate determining step?
The first one.
Yes, the first step, rate determining step. Once you make the cation, what's going to be the rate of the second step compared to the first? fast step. It's fast compared to the slow step. The rate determining step is the slow step. Because it's slow, it determines the overall rate. Okay. Of the two reactants, how many are involved in the rate determining step? Well, what was the rate determining step? This ionizing, was hydroxide involved with this?
No.
No, so how many are involved?
One.
One, that's why it's called Sn1. We just did an Sn1. What does that mean? Substitution by a nucleophile unimolecular. One molecule involved in rate determining step. That's what an Sn1. We just did an Sn1 mechanism from going from that to that. It's a substitution mechanism. We're going to learn two substitution mechanisms, Sn1 and Sn2 below. Okay, what do you not like about this mechanism? Do you think this is it, or you don't like it for some reason? Why is it not good? You don't like carbocations?
No, and it's a primary.
Well, I would not say no. I like tertiary carbocations. They're readily formed. You see them a lot. Secondaries, okay. But I don't like primary carbocation. Never form primary carbocation unless you have to. Well, when do I have to? Mass spec. We're going to see primary carbocations in mass spec a lot. Because mass spec is a very high energy process. And most mechanisms never do primary cation. Unless you have to, well, I can't do anything else. We can do something else here, okay? Bad. Primary cation, bad. You see, it's bad because I drew it here, but guess what? Primary cation is really up here. And you really got to do, you got to have a lot of energy, and usually you ain't going to do it. Right? Secondary, tertiary though gets down here, they can be formed. Okay. All right, let's try another mechanism, Sn2. How can we do this another way and get the same outcome, but a different mechanism?
Have the O kick off the DR. This is partial positive.
Here's another way. These electrons could just come in here and kick it off. Is that it? What does that arrow movement give?
The products.
All those two arrows give products. Everybody see that? Yeah. There you go. There's your mechanism. How many intermediates?
None.
0.
There's no intermediate there. Does this mechanism have a carbocation
No.
intermediate? No, we just said there's no intermediate. But to clarify, there's no carbocation here. So we did not form the bad primary carbocation. Up here, we understand why that would attack a carbocation. Negatives like positives. Why would this attack this carbon? That's not a carbocation.
It's partial positive.
But it is a dipole, and it is partial positive. Which would be easier? Hydroxide attacking a carbocation or attacking a partial positive? Which should be easier and faster? Tell me again? Why would attacking a partial positive be easier than attacking a full formal positive? Physics,
It's gonna want the carbocation.
here's a minus, here's a plus, and here's a partial plus. Physics, which one would this be more attracted to? Full plus or partial plus?
The full.
Full plus. This should be greater attraction. Thus, it's going to be easier to come together and make the magical bond. This is going to be more difficult than attacking a carbocation. But it still can be done. More difficult meaning in practice, maybe this requires heat. Maybe it requires longer reaction time. All right? You cook a hamburger, it takes 10 minutes. You cook a roast, it takes 2 hours. More difficult to cook the roast. All right? Understand? This is partial plus and how it's going to be a little less reactive, a little more difficult, but it can be done. All right? Reaction coordinate diagram for this. Let's call this A. There's no intermediate. Let's call this B. Let's put A here. We put B here, remember? Well, before this was called C. What do we got here?
A lower application
We just have an activation energy. Now, I don't know how high. I could have drew this higher. Okay? You know, just like the before, I could have drawn this like this. This could vary. You said low. It may not be low, but it can be done. But what I'm showing here is there's no intermediate. There's just a transition state. All right? Of the two reactants, how many are involved in the rate determining step? By the way, which is the rate determining step? That step. Now I've got two arrows. Does this all happen at the same time?
Yeah.
Yes, it's concerted. Okay? Incoming, out, all at the same time. It's just one step. That is the rate determining step. There's only one step. This is it. Are both involved in the rate determining step?
Yeah.
They better be, because it's only one step, and if they ain't both involved, then something ain't reacting. Yes, they're both involved. It's a substitution by a nucleophile, but it's bimolecular. Two things involved in the rate determining step. There is an Sn2 mechanism. Sn2 does not involve attacking a carbocation. It involves what? Attacking the partial positive, and we can also say it involves backside attack. And that implies we're kicking something off. It's a concerted kicking off of the leaving group. We did this some with alkene chemistry. Now with alkene chemistry, I actually call it backside attack. Books will not use that term in that chapter. They only will use the term when you get over here. I don't understand why. They don't think you can handle the term over there. When you kick off a leaving group from a carbon, we did that in alkene chemistry, like bromonium leaving group, and it's backside attack. That's how you know your stereochemistry. Yes?
So will the activation energy for the bimolecular, will that always be lower than the unimolecular?
No. Because I drew this low? No, I could have drawn this like this.
Okay.
Either way, I mean, I didn't worry about it. All I was trying to show here is that there's no intermediate.
Okay.
If you look back at the kinetics, thermodynamics handout with the reaction coordinate diagrams, you'll see this one in there. You'll see all the ones we've been referring to in there. All right? Go back in that handout. I showed you one at the very end that had no transition state. It probably at the bottom said Sn2. I didn't even say that then because it wasn't relevant then. Okay, there's an Sn2. Let's look at this reaction here. This reaction is an Sn2. How do we know this? We have to look at this and say, I would never make a primary carbocation. Leaving group would never just leave and make a primary cation. So by default, it must be an Sn2, not Sn1. And we would do the mechanism like there. Question down here. I've kind of already answered this a little bit. We'll go through it again. Kinetic studies. Proving mechanism. I've already told you it's Sn2. That can also be proven by kinetic studies, which you can do in the lab. And if you do it in the lab, you will see that the above reaction can be affected by changing the concentration of either the alkyl bromide or the hydroxide. You change either one and you'll change the rate. Rate can be changed if you change either one. Since rate depends on concentration of both substrates, each must be involved in the rate determining step. Since they're both involved in the rate determining step, it must be bimolecular. And that's how you would prove that it's Sn2. You would do rate study and say, okay, if I change the concentration of this, does the rate change? The answer to this reaction is yes. The answer to this is yes. Either one, you change and the rate changes. You can determine that in lab. That tells you that both are involved in the rate determining step. If this was not in the rate determining step, then changing its concentration would not matter. Does that make sense? I've got more of it so that it's going to react faster. So what? That ain't the rate determining step. If the fast step occurs even faster, sorry, that doesn't change the rate. The slow step affects the rate. It's like if you ever go to eat at S&S and have to stand in the line. That's the rate determining step. You're not gonna get your food faster by running to your table after you go through the line. It don't matter how fast you do that. You still got to sit through the slow step of going through the line. All right? Speeding up the fast step does not speed up your overall rate. All right? Which reaction matches the above kinetics? Sn2. What is the rate equation for the mechanism? You did rate equations? Rate equals what? We know it's Sn2, so it's what? K
Concentration.
times concentration of this times concentration of what?
Hydroxide.
Yes. You see? They're both involved. You change the concentration of either, and you'll change the overall rate. That's what we're saying. What is K? That's something, I mean, yes, it's called rate constant, but what is it? How does K vary? What? Yeah, the temperature. Because higher temperature will make this faster, but it doesn't change concentrations. So what does it change? It changes K. What else is built into K? Things like reactivity. For example, if I change this to iodine, which is a better leaving group, what does that mean? It leaves easier. That means K is going to be bigger if it's iodine, because K is your inherent reactivity that's there. K changes according to the reactants and stuff. There's a lot in K. But then you also multiply it by concentration of your reactants. Those that are involved in the rate determining step. And in Sn2, they're both involved. If this was Sn1, it would only be what? Some type of K times just that, right? If it was Sn1, you would not have this. Okay, I'm presenting both of these mechanisms at the same time, together, so we can compare them easily, as opposed to let's only do Sn2. Okay, now let's only do Sn1. I don't like doing it that way. I like making comparisons along the way immediately. All right? When you read your chapter, the first half will be on Sn1, the second half will be on Sn2. All right. Now we will focus on Sn2 a good bit early on, but along the way we will be always comparing it to what an Sn1 would be, or vice versa. Okay, let's get into it here. Let's take a quick 2-minute break first, and we'll get back at it here.
Stevens, I was wondering if we were gonna have any, review things like how we did for test 2, if we're gonna do that for test 3 or the final exam? Or if you weren't sure yet?
I don't know if Friday's a good day for review, but the test is not till Wednesday, so it doesn't make it as ideal. I'll examine, there's review questions in the lab manual, in the workbook. We might can, we only have one day between.
And I think that one day is, we have a lab that day. That's our last Thursday lab.
Thursday. Quick turnaround there.
Do you know when our group lab reports are gonna be due?
A week from when you did the lab, so
Okay. I got it written down.
next.
For us, it'll be next Tuesday.
Next Monday, Tuesday, right?
Monday, Tuesday, yeah, Monday, Tuesday. Okay, today we're doing Diels-Alder reaction in lab. Any questions about that lab?
Which lab are we doing next Monday and Tuesday? Because the one on the syllabus, I don't see it in this lab.
I thought it was shaken, not stirred.
Okay.
And that was in the lab manual.
Yeah, I think it's just called something different on the syllabus.
What's it called? Okay, yeah, generic. Monday, Tuesday, it says nucleophilic substitution lab. That is the shaken, not stirred.
Okay.
Monday, Tuesday is shaken, not stirred. Okay, determining mechanism by stereochemistry. If you take this substrate here, which has some stereochemistry, reacted with KOH. Okay, by the way, this is a spectator ion, organic chemistry. Anytime you see this is hydroxide, right? All right. You react this with hydroxide, we can do a substitution reaction. Br minus was the leaving group. You see Br minus here, right? I just have K pluses shown here. Anytime you have a minus, you got a plus, so we can just sit there. Substitution reaction, yeah? But if this is R, and it is, we know that you get S only. And this product would be optically active. With alkene reactions, we said you never can make an optically active product. That is, unless you start with something optically active. But this is optically active. So it's just one enantiomer, or R only. So we're not breaking that rule. This reaction is said to be stereoselective, stereospecific. R is, whatever this is, you're getting one stereoisomer. And since they're enantiomer, it's enantioselective. We call this complete inversion. Inversion. The configuration around the carbon is said to be inverted. R going to S. The fact that we get inversion tells us it's which mechanism.
SM1. Or no?
Which mechanism, SN1 or SN2, does the stereochemical outcome support? SN2.
Yeah.
Which means what? Hydroxide does what?
Kicks it.
These electrons, that leaving group is going back, so how do these electrons come in?
From the front.
Front. Now I have a flat board here. I can't show something coming in directly from the front. But we have to know that it's going back. So it comes in from the front, so the hydroxide should now be front. Okay? Backside attack gives inversion. But we've seen that before, right? Yes. The outcome, SN2. If it was SN1, what would the product be? Would it be S or R or what?
It'll be either.
Yes. It would be both. Because SN1 would be making a carbocation. Once you make a carbocation, how do you attack it? SN1 would be racemic. We didn't get racemic in this reaction. We got inversion. That means, that tells us the mechanism must have been SN2. Okay? We didn't answer the first question. Is SN1 mechanism more or less likely for this reaction compared to previous?
Isn't it more likely because it's going to form a tertiary carbocation?
Wouldn't be tertiary.
Or secondary?
It'd be secondary. If it made cation, is that more likely than the previous?
Yes.
Yes, it's more likely than the previous. Secondary cations are okay. They're not as good as tertiary, but they're okay. Yes, it's more likely. But seeing the stereochemical outcome, what was the mechanism here? Even though SN1 is more likely than before, it still ain't the mechanism. The mechanism is SN2. Main point here is your stereochemical outcome can tell you what mechanism took place. All right, inversion. Let's look closer at how inversion is obtained. 5-coordinate transition state. Here's the same compound. That's it here. That's the same exact compound. I just got the H drawn in and it's turned a little bit. It's still R. Hydroxide. Here's the carbon, tetrahedral carbon we're attacking, right there, yeah? The bromine is that way. How does the nucleophile come in? We're doing SN2.
Opposites. Yeah, the opposite side.
Opposite side, we call that. We call that backside. This comes in and comes. The methyl and the H are like this. This comes right between them. And we're going to attack that carbon. And we're going to kick this off. Yeah? So let's look at the transition state. It's going to be, I'm going to draw the carbon in, I think, the carbon we're attacking. This bond is being made. It doesn't go completely from not there to there. There's a transition state where it's forming. I'm showing that here like it's forming. This bond is being broken. So it goes to a point where it's sort of partially there, not completely broken. This is often put in brackets. Sometimes you see like a double dagger up there or something, indicate it's the transition state, or sometimes called activated complex. Charge though. What's the charge of the hydroxide here? When we're done, it's going to be neutral oxygen. Starts as negative, it ends as neutral. What is it as the bond is forming? Partial negative. The bromine is neutral, it ends up as full minus. What is it as it's partly? Yes. Charges like this sort of in that transition state. There's your transition state. Importantly, though, the H and the methyl are supposed to be eclipsing. They're right in front of each other. And the three bonds around here, one of them I got straight up. Here we go. One of them straight up. The methyl going back, and the H is right in front of it. Okay? I'll make it two, a single bond, but I mean easier for me to hold my fingers like this. Okay? Or the arms. The H is right in front of the methyl. That's what it's supposed to be here. What is it? What is this geometry of the pin and two arms?
Trigonal.
Yes, it's trigonoplanar. It's all planar here. What's the bond angle between the pin and the arm? It's 120. What type of hybridization does this look like for this carbon?
SB2.
Yes, but what was the hybridization over here? sp3. This is an sp2-like character. Okay? With bond angles of 120 degree between the three groups. Not here, that's a 90 degree bond angle. But between these three groups, it's 120. Now when you have a trigonal planar, okay, again, trigonal planar, boom. You know, usually we draw like that, trigonal planar. But if you take this and turn it like this, then these two will be like this right in front of each other, and that'll be still straight up. Alright? Or if I take that and turn it, I got one of these partial bonds this way and one of these partial bonds the other way. Whenever we draw a trigonal planar, what else is on the carbon? sp2. That we're not drawing. Day one, trigonal planar. Here it is. What else is here?
Lone pair, right?
A p orbital. P orbital, right? sp2 has 3 hybrids and a p orbital. Okay, the p orbital would be perpendicular. This is almost like a p orbital here. perpendicular to the trigonoplanar. In the end, it has a lot of sp2-like character. Importantly, bond angles are 120. What are the bond angles over here? 109.5. Thus, well, I did it between that and bromine. Let's do it between this and methyl. Because over here, that and bromine is 90. That's not really part of the sp2. The groups are 109.5. What happens in the transition state? The angle between the groups.
They get bigger.
The angle has to get bigger. Yeah? Make sense? Okay, how does this complete? This bond completely breaks. Okay? This completely forms, and this electron sort of pushes these electrons out. And so what do we end up with? Carbon here. The OH is now here, and that's completely formed. That's now a neutral oxygen. These groups now get pushed this way. They're still the same, still H. Well, let me draw the methyl back directly. The methyl is back, and then we got an H. Okay? There you go. There's your product. This is R, and guess what this is? S. It's now said to be inverted. The inversion comes from the nucleophile attacking backside. But look at the inversion. See these three groups here? From the carbon, they're all kind of coming this way. When the nucleophile comes in, it straightens them up. Go planar. Then when this thing over here departs, these go that way, and I can't do my hand too much that way. Okay, they then go this way. Because when that departs, they have more room to spread out that way. And so my hand went from this that way. Think of it as an umbrella. The umbrella like this, sometimes your umbrella never gets inverted. Instead of hanging like this, it goes like that. Same thing. But if the umbrella went from this way, hanging over your head, you ever seen an umbrella go the other way? But when it does that, doesn't it have to pass through planar on its way to the other way? It's passing through planar as it goes the other way. But the other way, trust me, this is now S. We went from R to S. Sometimes I have to not tell you because I don't want to confuse things. It is inverted. And this is how the inversion takes place. We look at the transition state. Transition state knowledge can help you understand other things. By the way, why is it called a 5-coordinate transition state? Because right here, the carbon is coordinated to 5 different things. 1, 2, 3, 4, 5. It's not bonded completely to 5, but it's called coordinated, 5-coordinate. Pentacoordinate. All right, just because there's 5 things around the carbon. Transition state requirements can affect reaction rates. Both of these are substitutions. The I- is replacing the bromine. Which reaction is faster?
Top.
I'll give you rates. Why is the top reaction faster?
The bond angles are larger.
What?
The bond angles are larger, so it's easier to.
Have you been reading or
Yeah.
watching previous videos or something? Okay, good. You're right on point. Okay. The reason that this is much slower is, what is the current bond angle? Well, first off, when this undergoes a substitution, what type of angles occur during the transition state? Transition state has what type of angles around the 120. Yes.
Which carbon is going to be more likely to achieve 120 bond angles, top or bottom?
Top.
Top. Right now, this is 60 degrees from 9th grade geometry. How easy is that going to achieve a 120, which is what the transition state requires or is best? It's going to have a hard time getting 120. That's going to be much easier. Does it have to be exactly 120? No, 120 is ideal. Less than ideal is going to be slower. That's going to have a tough time getting anywhere up near 120. It's going to be quite slow to achieve the transition state. That reaction, you ask, I drew the transition state like this. That one's going to have a transition state like that. It's going to be much slower because it's much more difficult to achieve the transition state. So, that's the type of question you can answer by understanding the transition state. You can also understand something like this. I wish I had not erased it. Effective p orbital being immediately adjacent to the reaction site. All of these react much faster in Sn2. Same leaving group, so it's not leaving group ability. All of these have a p orbital next door. Okay? This is the carbon that gets attacked and kick off the leaving group. Okay? By the way, we are doing Sn2, right? P orbital next door. P orbital next door. P orbital next door. There's actually two next door here, but only one's going to be relevant. Look at the transition state. What would a p orbital next door do? You have it drawn. I'm going to try to redraw it. Didn't it look like this? Didn't we say a p orbital like here? Didn't we say that? Okay. You put this on your transition state down here where the ethyl group was, yeah? Or methyl or something? Or I think it was drawn up like this, right? Okay. What if there was a p orbital here? This could interact here. And that p orbital interacting leads to stability. Stabilizing the transition state. Okay? Because, right, when this reaction takes place, don't you have like a p orbital here? Okay? That makes those much more reactive for Sn2. So reactive that all these here tend to be toxic. Because they react so quickly with like the proteins in your eyes and the proteins in your liver, proteins that have like nucleophilic groups. On the other hand, this guy here is not as reactive. There's no p orbital next door. It will do Sn2, just not as easily. Maybe all these react at room temperature. This requires 100 degrees for a couple of hours. Because of that, it's also less toxic. It's not going to react as quickly with things in your body. No, I didn't say it was not toxic. I said it was not as toxic. Make sense? P orbital stabilizing the transition state. Taking it from here back down to something that's much more readily done. Okay. What are we under? What are we looking at? We got E's and 1s and 2s. What are we under? 1, 2, 3, 4. E. What is E? Reactivity of various electrophiles. What is the electrophile? Likes electrons. I mean, we got I minus. This is like a nucleophile. That's kind of like a positive. What is an electrophile like?
Negative.
Well, likes electrons. Likes negative. So what in this reaction likes this?
Positive.
Apparently this. It's partial plus, so it's going to like electrons. This is the electrophile. And that's the important thing right here. The electrophile contains the leaving group. Right? We're looking at the thing with the leaving group. That's what E is. And we're looking at how to determine maybe which ones are more reactive, etc. Things with leaving groups. Down here, effective carbon substitution. Okay? Reactivity of various things with leaving groups. This guy, I'm keeping the leaving group the same here, so we're not looking at that yet. There's no change. The change here is what? Substitution on the tetrahedral carbon that gets attacked. Again, we know that this is CH3. Yeah. Here the carbon has one carbon group. Here the carbon has two. Here the carbon has three. So the substitution at the tetrahedral carbon is increasing. This is more reactive. Why? Because when the nucleophile comes in, these H's are real small. Don't redraw these, but just for the effect, they're pretty small. And this guy can come right in here and get right back in there. On the other hand, when you start putting these carbons, well, they also have H's. All right? You don't have to draw on this, you get the point. And the nucleophile tries to come in, whatever it is. It's like, here we go. I was trying to squeeze through there. That's going to be slower. Crowding, we call this sterics. Steric crowding. Okay? You see the difference? No steric crowding. That's a little bit more. Okay, here's a take home. This is called a tertiary halide. The halide is on a tertiary carbon. Never do Sn2 with tertiary halide. I put never in capital letters, so maybe you would remember. Now we'll see other leaving groups. You can make this more generically Lg. If the leaving group's on a tertiary carbon, never do Sn2. All right? Which one's best? Here. Toxicity. Of these three, of these up here, which one do you think is most toxic?
The first one.
Yes. Because it reacts so easily with any nucleophile in your body. Because it has no steric hindrance. Methyl bromide's a gas. Because it's so small. Methyl bromide is used to fumigate, kill like roaches and rats and stuff. Now it's not used in your house because it's a gas, but they use it in like huge warehouses. You know, like a huge warehouse that's the size of a football field. They'll just go in and gas it with methyl bromide, close it up, and then they come back and all the roaches and rodents are dead. Because they inhaled it and reacted all the molecules in the body and did Sn2. This is not as toxic. A little bit, you don't, I mean, okay. Less reactive, don't react at all. At least not by an Sn2, because right now we are looking at Sn2. Question, we do know Sn1. Which of these four would react quicker with Sn1? Tertiary, because we know why. What's the rate determining step for Sn1? Carbocation formation, which is going to form carbocation easier. This reacts faster in Sn1. That's what I said down here. But you knew that already. All right? Here's just a table with some rates. Same reaction here, except we're using lithium as the counter ion, counter cation. I minus replacing Br. You see the rates. this one being listed as 1, that being faster, this being slower. Negligible, or basically no for us. Okay, just call it no. Tertiary. Again, this is by Sn2. We can discuss why that is an Sn2 and why it's not Sn1. We'll do that in due point. Trip to the dentist. I know at least one of you is pre-dental, yeah? Somebody? Okay. Trip to the dentist. Anesthetics. Anesthetics vary depending on how long they act. Some anesthetics are short-acting. They make your mouth numb for 30 minutes, 10 minutes, 30 minutes. Others are going to make you numb for 6 hours. Okay? Why? They last, the length of how long they last depends on how quickly they're degraded in the body. They're degraded by chemical mechanisms. Okay? And the mechanism takes place around the carbonyl group. Okay? More crowding around the carbonyl, the slower they're going to be degraded. Because the reaction's slower with all that crowding. Slower they're degraded, the longer they last. If you look up these on Wikipedia, I mean, you can find a list of anything. Look up local anesthetics on Wikipedia or something, and they'll probably give you a list of them with structures. And you'll see, the shorter acting ones, the carbonyl is not sterically hindered. It's accessible. The longer acting ones have all this groups around the carbonyl, crowding. That slows down the metabolism, makes them last longer. Okay, so that's an application of the idea of steric hindrance. Sterics is very important for Sn2 reactions. All right. F. Now let's look at leaving group. It's still the electrophile, but instead of focusing on carbon, I reckon, for some reason I changed it to F. Still the electrophile. Leaving group ability. We've already said that iodine is your best leaving group. We try to do this with this. By the way, what's the nucleophile? Let's get rid of these ions, right? The spectator ions, and this is what? O minus? Right? You got to know that. Spectator ions. This nucleophile can replace the iodine. We can make this bond here. Iodine has been kicked off. That's a pretty easy reaction. Okay? That would be Sn2, because this is primary. If this is an F, though, F is not a good leaving group. It's going to be very difficult to impossible. It would be a bad reaction. Why? Why is iodine such a better leaving group? Well, let's look at it. I versus F minus. Lone pairs are here. Which is more stable? I minus, much more stable because it's larger. See, I minus is much more willing to leave and become bent. F, even though it's the most electronegative atom, it's so small. It's a little bit counterintuitive. You might, again, should this be eager to form? Actually, no, not compared to that because it's small. The size makes this actually more stable. And thus more eager to serve as a leaving group and go and take the lone pair and become minus. All right? What about other atoms? Can atoms other than halogen be leaving groups? What about oxygen? Try to do the same reaction here with methoxide. Replace the hydroxide This comes in here and kicks that off. No reaction. What does that tell us about the OH group? Bad leaving group. If it was an iodine, it would work. Good leaving group. Bad leaving group, bad leaving group. Hydroxide will not act as leaving group in a slow rate determining step. Why do I say slow rate determining step? Because it actually will leave in a fast step. When you get to organic 2, you'll see leaving groups leave in fast steps. And hydroxide can leave there, but it cannot leave in a slow rate determining step. So at this point I can ask a question. We know two mechanisms, Sn1 and Sn2. In which mechanism does the leaving group leave in the rate determining step?
This is a long one.
Does leaving group leave in the rate determining step of Sn1? What is the rate determining step? Leaving group leaving, ionization. Yes, it leaves in the rate determining step. What about Sn2? It only has one step. It must leave or you ain't doing anything. In both of our mechanisms, the leaving group leaves in the rate determining step. Hydroxide is not a good leaving group in either mechanism. In organic 2, you will learn substitution mechanisms where the leaving group leaves in the fast step. In those mechanisms, hydroxide can leave. Because the fast step is an easy step. And since it's easy, okay? That's why I clarified this. Now, how can we make oxygen a better leaving group? We can do that. If you protonate it with acid, well, that's what protonation means, proton. Put a proton on it, protonate it. We take this, we also have to have a neutral nucleophile. Neutral. This reaction will work and we can get the same product. How does this work? We first protonate the alcohol with strong acid, okay? Strong acid. Just an acid-base reaction. We just did an acid-base reaction. Good old mechanism for acid-base, right? Now this will be a good leaving group. But instead of hydroxide ultimately leaving, what is going to leave here? Water. Now the nucleophile, even though it's neutral, come in here, kick this off, and water can act as a leaving group, not hydroxide.
Does the nucleophile necessarily have to attack first before the leaving group leaves, or can the leaving group just leave on its own, like an Sn1 reaction?
No, at this point, this is just a leaving group. And things with leaving groups can operate by two different mechanisms. And so this gives, but we're not done yet though. That doesn't give that. What does this give? What's now bonded to this carbon? Oxygen, and it has what? A methyl and what else? H, how many lone pairs? 1, and a plus charge. Plus water. That's the leaving group. Now how do we get from here to here? Something's got to take the H, go neutral. Well, there had to be a minus here. Maybe it's HSO4 minus. And if we these electrons take the H and leave that behind, we get the final product plus what?
Water.
No, we've already made water. What are we making here? H2SO4 reformed. So what is the strong acid? Catalyst. The H plus is catalyst. What did the catalyst serve to do here? It made the leaving group better. And then it was reformed. It did its job and then it was reformed. Catalyst. A strong acid catalyst. We just did, what type of mechanism did we just do? Sn1 or Sn2? Right here is the Sn2. But then students say, well, I thought Sn2 didn't have any intermediates. Well, it doesn't. Here's the substitution. This step was an activation of the leaving group. There's no substitution here. And here we just lost proton to go neutral. So the simplest Sn2 will just be one step. This is also an Sn2, but it had other steps associated with it. Making the leaving group better had nothing to do with the substitution. Okay, so hopefully you see that. So in the end, how do you make oxygen a better leaving group?
Hit it with a strong acid.
Protonate it with a strong acid, then it can become water, and water will be the leaving group. Positive oxygen leaving to become a neutral oxygen is way better than a neutral oxygen leaving to become a negative oxygen. That ain't going to happen. In the shaken not stirred lab, we will make OH a better leaving group with acid. Monday, Tuesday. Okay, why did we have to use a neutral nucleophile? Back over there. Methanol was neutral, not the anion. Why can't we use the anion? Why can't you do this like this? H plus to make this a better leaving group, and then we can have this come in and kick off the water. Why does this not work in practice?
You don't reform stuff,
That doesn't mean it wouldn't work. That would just mean you need a lot of catalysts, and it would no longer be catalysts. It would still work though. You would just need a stoichiometric amount of acid. But it still wouldn't work. It doesn't work because you can't have your cake and eat it too. Strong acid means acidic conditions. O minus is the same as like, if that was an H, what is that? It's hydroxide. Well, methoxide is a base just like hydroxide. I know they don't tell you that in Gen Chem. I don't know why. In Gen Chem, you learn that this is a base, but you never even discuss that that's the same exact thing, just with a carbon. These are identical. They're both same pKa's. Okay? Can you have acid and base in the same reaction? They're just going to react. The O minus will just react with the H plus. You can't have both. It's just like if you put hot and cold water into your tub, it's going to neutralize and the water will just be warm. Can you put hot and cold water in your tub and then say, okay, I'll reach in and get the hot, and now I'm going to reach in and get the cold? Oh, neither one will exist any longer. It's now warm. They have neutralized and neither one exists anymore. right? You can't do that. So you have to use instead the neutral nucleophile. Because it will not react with the H+, at least not fully. Okay? Now this is a common reaction of alcohols, right here. A common reaction is to react them with HX, like HI, and you can get this. Convert the alcohol to an alkyl halide. Very common reaction. Mechanism. Well, let's consider this H plus I minus. Is this a good leaving group? No, but we have acid present because HI is a strong acid. We can protonate the OH, then the I minus can come in here and backside kick it off, and what does that get? There you go, you get your product plus water. Here's a question. And guys, there's lots of questions I could ask you at any time. I should never be able to have discussed this before, but I ask you, and then you rationalize it. In that reaction, is the H plus a catalyst? The H plus is making the leaving group better.
But you're not reforming.
But we're not reforming it, are we? Did we reform H plus anywhere?
No.
Water is not a strong acid. If we had reformed HI or something, it's not. In that case, H plus is actually not an acid catalyst. But it's still making the leaving group a better leaving group. It's still doing something. It's just not formally a catalyst. Common reaction of alcohol. In organic 2, you'll look at the chemistry of alcohols closer and you'll see this reaction. Hopefully when you get over there, you'll be good to go. All right. Here we go. In addition to OH groups, OR groups can also be made to be leaving groups. This OH, here OR. And by the way, you've got R groups on both sides. Can you show a product of this reaction? Predict a product. Predict a product. By the way, this whole handout is on substitution reactions. So maybe I could say this. Predict a substitution product. Yes?
I was going to ask you.
You got something? Not right. Not right. You had a choice there, and you didn't choose wisely enough. No, you had a choice there, and you didn't choose wisely enough. Somebody else got something? No. I'm seeing all three of y'all had the same exact thing. Nope. Why are you all doing that? I really want to know. I would turn to the first page of this handout and read the heading of the handout. It's in bold, capital letters. Somebody read the heading.
Provide a detailed stepwise.
No, I'm sorry.
Oh.
Not the warm-up page. It's underlined. It's at the very top. Nucleophilic substitution at what?
Oh.
Okay, there we go.
Gotcha.
Okay, can I just protonate this without having to go through a complete mechanism?
Yes.
Okay, now on quizzes, tests, etc., you gotta do complete mechanism. But let's save a little ink here at the end of class. All right, everybody know how we got there? Protonate, we got Br minus. Okay, can this act as a nuclear? Do we have a potential leaving group? Yes, a positive oxygen. It didn't have to be an OH originally, it was an ORs. Or group on both sides. Okay, now is the oxygen going to leave from this carbon? Are we going to attack here and kick it off of that? Or are we going to attack here and kick it off of that? Everybody I saw attacked over here and kicked it off of there. I don't know why. That's not a tetrahedral carbon. This one is. These electrons attack here, kick the oxygen off, and what is the product? That there plus what? Plus that. This whole thing was what in the reaction? That was your leaving group. That's phenol. That's actually a big, pretty, it's a major tetrahedral carbon. That's your only choice. We do not do Sn1 or Sn2 at this type of carbon. We only do it at what type of carbon? Tetrahedral. We could explain why over here, why. One reason why, if it did attack here, which bond are you going to break? The sigma bond or the pi bond?
I don't know.
Pi bond is weaker. The weaker bond should break. Why would the stronger bond break before the weaker bond? And it's things like that. And I can tell you other reasons. No. Tetrahedral carbon. Okay. No? I'd really like to know why everybody attacked the other one. Is there a certain thing you're thinking? Is it because it was bigger over there?
Well, everything up until now we've
It's probably because it's on the left?
Yeah.
Just
I should start. Well, that's what I did over here. I drew that. I would have drawn it like this. I drew it like this because these carbons and the bromine is on the left, so I thought, well, I'll draw it like this to help get. Are you telling me if I draw it like that, you would have been okay? I don't know. No, I don't. That's not applicable. Okay, tetrahedral carbon. Okay, we're about done here. B. Can you make OH a better leaving group any other way? Protonating it is the most common. Let's keep it broader. It doesn't have to be OH. It can be OR. Just oxygen in general. Can you make oxygen a better leaving group any other way?
Yeah.
Particularly OH. We'll pick up here next time. Tosylates. You can convert an OH to a tosylate. And a tosylate is a good leaving group. Okay, Diels-Alder reaction.